But I'm gonna try to learn it here first.
Alright, you guys ready for 0 minutes? I love this whiteboard, bro. It's so nice.
Dude, this bait study room is actually better than the thing. Dude.
Yeah.
Yeah, it is pretty nice.
What?
Can you please come here tomorrow?
Me?
Yeah.
I might come here to code.
Yeah, lock in, bro.
Alright. Okay, so this is what's called a finite group. Okay? And specifically, this is what's called a cyclic group. So just like fields, right? So a field is basically a set with like a bunch of properties, right? A group is also a set with a bunch of properties. So remember what a set looks like. 2, 3. This is an example of a set, right?
Yeah, no repeating elements.
No repeating elements, right? So this is an example of a set. So it just follows a bunch of elements, right? So for example, you know that if this is, I wrote this wrong. If this is the set of natural numbers, right? You know that you take any element, so 1 plus 2, that's equal to 3, right? You take any two elements in here, and the elements, if you add them together, or you multiply them together, they're gonna fall into the set. That's called closure. So when you hear like, in linear algebra, like, oh, this thing is closed under like this, closed under addition or closed under multiplication, like that's what it's referring to. You take any two elements in the set, you do something to it. This is what's called binary operation because it takes in two elements of the set. You do something to it and you still end up in the same set.
S
Does that make
cross
sense?
S maps to S.
Exactly. So in this case, you know that the function takes an n cross n and it maps back to something in n. Right? So addition is an example of such a binary operation.
That's how they define it in abelian groups.
Exactly. So this is also an example of Billion group.
Yeah.
But the terminology doesn't matter too much. I don't want to confuse you here. So addition and multiplication are examples of this.
Division and subtraction are not.
It's not because
yeah,
you don't. If you divide 1 over 5, it's not going to be in a natural number.
Same thing if you did like 1 minus 3 or something.
Exactly. 1 minus 3 is also not in the set of natural numbers.
Wow.
Wow.
Actually, it
So
is, but like not in this. Oh well. Oh no.
It's not in the set of natural
Yeah,
numbers.
I read it as R, not M.
Alright, great.
Yeah.
So we just went through Math 295 Lecture 2. We don't have to explain any more than that since you guys already get this. But okay, so let's look at an example of what's a cyclic group, right? So here's an example of a cyclic
Dude, I haven't
group.
been recording it.
Huh?
I'm just gonna post this on YouTube.
Alright, fair.
Here's an example of a cyclic group. You guys ready for this? This is pretty cool. Finitely generated. Alright, so let's say you take the group with element. Okay, I'm gonna do something more general. Let's say you have a group with an element G, right? So in this case, it's the element 4 because you're taking I to the 4th power, right? And here's what that looks like. You have a group, just like algebra, you start with group to the 1st power, then group to the 2nd power, then group to the 3rd power, and so on and so forth, right? So let's review what this means. G to the 3rd power does not mean you take a number to the 3rd power. It means G something operation, G something operation, G. Does that make sense? It does not mean you take G times 3 times G 3 times. It means G has an operation with one thing and has another operation with another thing. Right, so to the 4th power, it would be another one of these operations.
Such that the closure falls into that same set.
It'll be the closure, yep. So let's look at an example here. The example with I, right? If you have something like 4 and you define this group that's generated by I, so you always have a finite group, you have to generate this from somewhere. So somewhere that's generated from I, right? So here's an example. You have I to the 1st power,
Yeah.
right? I to the 2nd power, I to the 3rd power, I to the 4th power, right? So why do I close it here? Well, I to the 5th power is the same thing as I to the 1st power, right? I to the 6th power is the same thing as I to the 2nd power. I to the 7th power is the same thing as I to the 3rd power.
Is the bracketed for the cardinality?
This?
Yeah.
Oh, this is a cyclic, finally generated cyclic group.
But
Yes.
like, doesn't it like denote how many elements are in it?
No, it just means what power you have. I guess, yeah, that's actually a theorem. So the order, so this is actually a term. The order of G, so remember what G is. G is this thing right here, right? So in this case, what is G?
4.
G is equal to 4.
Denoting that there's 4 elements before they start repeating.
Exactly. In the finite group, G is defined to be. Alright, so you have this little curly O of G, and that stands for order. It says it is the minimum number such that G to the M is equal to the identity element. So let's look at what that means, right? Suppose that this is the identity element.
Identity element is like 1 or 0.
So if you treat this as the identity element, do you agree that I to the 5th power gets you back to that same identity element?
Yeah.
Okay, so it is the minimum number of times you have to go around to circle back to identity element. So if this was the identity element, you have to go around 1, 2, 3, 4th time to circle back. So what is the order of this group?
4.
Exactly, so O of G in this case is 4. How? It is the minimum number such that G to the M power gets you back to identity element. Does that make sense?
Could you explain how that works with like I2? So you're just going 4 to the right?
Yeah, because you do I2, I3, I4, I5.
Oh,
and
I see. And then
I6.
you could, any of those values can be the identity element because it's cyclic.
Exactly.
Yeah.
So
Okay.
I could treat this as I2, and I3 is also the identity, and so is I4. But
Okay,
you
yeah.
go around, the order is the same for all of them.
Makes sense.
Does that make sense?
Yeah.
Wow, you guys have learned.
It's kind of like modulus almost.
It is like modulus. It's exactly like modulus, and that's the whole idea of algebra.
Like when we did the homework too, it was something like this but with abelian groups, and I did it by defining an addition with mod 2.
Oh, that's interesting.
I don't know if I have the.
Yeah, this is modulus. So modulus.
This is exactly modulus. You go around the group. So complex numbers can map to finally generated symmetric groups. It can also map to modulus. It can also. Did you know this is determinants?
How so?
You mentioned that earlier. But
Yeah, you mentioned it earlier.
So
but-
how does
you
this
mentioned
have
it before.
anything to do with determinants, right? All right, I'll tell you how. Oh, the proofs actually get really interesting here. G of D is the identity. There's a thing called Lagrange. So okay, so basically, determinants rely on 2 things.
The Lagrangian.
Actually, 3 things. The Lagrange theorem
What's the Lagrange theorem?
is not the one you learn in calculus. The second thing determines, what is it determine on? Determines on what's called orbits. Cyclic finitely generated groups. I remember her teaching this in 296 and I was just like, what the fuck is she talking about? This whiteboard is really fucking good. What brand is this? Just say I'm here. Okay, need to go back and do some code forces. So it depends on these 3 things. If I were to teach you this would take an hour and a half,
Fair enough.
right? But I'll give you a preview next time. If you have more time to me, I'll teach you all this. So you actually understand what determinants are. I can send you my notes. I don't know if it make any sense. Like my notes are like this. Wait! You guys know orbits already. I don't have to teach you orbits.
I've never heard of this.
You guys know orbits. Alright, so, you guys remember learning about, does all of this make sense?
Yeah.
Yeah, this.
You understand what orders are? So we're already down 1, okay?
Wait, so the question was define operate. So let F be a field that's just 0 and 1, right?
Okay.
Sorry.
Which is the valid
set,
field?
set. Yeah.
Which is the valid field?
Define operations plus and the times the dot on the set that makes it a field and prove that there is no order on the relation F cross F that makes it an ordered field. So I defined addition and subtraction in mod 2. Sorry, not and multiplication in mod 2, and I just did like a lot of casework to show that it doesn't meet the axioms.
Yeah. Here's a symmetric group. Okay? So S of n, remember 465?
Sterling numbers?
You remember 465 when you guys wrote this? Or like this? What does that stand for?
Permutations.
Permutations.
Alright, so it's 1 up to some number n,
Yeah,
right?
yeah, dude, like the permutations and this kind of stuff is all applied group theory.
Alright, so let's take a permutation, sigma, that's why there's a sigma, right? Of the symmetric group. Okay. Here is an example of how this is. Okay, you just have to take this theorem because I'm not gonna prove it. It takes a while to prove. But every single permutation can be written
This is bus, bro.
as a product of transposition. Alright, so this is what that means.
Yeah. Oh yeah, dude, she did something like this in one of the lecture.
T1 up to times tk. That's what like for example, like you can write a permutation as like 2,
Transposition
3,
is
6,
Yeah.
1, 2, 2, 3, 6.
Like remember?
Oh, the
one-
mappings,
This is the
the
one we're talking.
mappings.
This is the one we're
I
talking
remember this.
about.
She like drew like the vertical
She
line.
drew a little mapping? Okay,
No,
so
no,
that's what
dude.
that's saying.
And then she did something about this with graph theory, and she was actually using matrices with it.
It's a matching, bro.
Yeah. Oh yeah, the matching. Oh,
It's literally a matching.
I didn't hear that.
It's a matching.
Okay,
like-
so
Yeah.
A matching is just a permutation, bro.
exactly, matching
Yeah.
is just permutation. So today you're gonna learn about orbits, groups, and orders. You're also gonna learn about group actions. So here, this is like 4 chapters in abstract algebra of a 16-chapter book. So you guys are already like a 4th way done with abstract algebra.
Damn.
Cool. All right.
493.
Okay, so think about a permutation. So let me give you a permutation. So let's say you have something like this. 2, does that look familiar? Last time I taught you this?
Yes.
Looks awfully familiar, huh? Alright, and
That-
suppose
that
that
one
you take a set 1,
Dude,
2,
that is legendary.
7, and 8. Okay, great. So we want to think about. So remember this notation. What does that mean?
That's the
That's
finally generated group.
Finally generated group of this particular element, right?
Yeah.
So this particular permutation, that's finally generated from here. Okay, I want to think about this as acting on n of 8 or here. All right. So what does acting means? It means that instead of having that as something like this, that's fine. I'm gonna do something to all these elements like chemistry and put them together. Okay? So here's what that's gonna look like. So when you put them together, there's something called orbits. Okay. So this is how you read this notation. I learned this correctly in fucking 296 this time around. Okay, I didn't fuck it up. Last time I fucked it up. Okay, let's look at the element 1. So when you apply this to this permutation, what happens to 1?
One maps to itself.
1 maps to
Yeah.
itself, right? So you know that there's a self circle, and this permutation, which is you can just think of as a function at this point, acting, right, on this group, and it's gonna map to 1. Make sense so far?
Yes.
Okay, great. Now you see how there's this little weird tidy group right here that puts 2, 3, and 4 together and put them in like parentheses, right? So it almost tells you should go around. Does that make sense? So if you have a 2, where does 2 map to?
3,
And where does 3 map to?
4,
And where does 4 map to?
2.
Exactly, back to 2. And 2 maps to 3, 4, and back to 2, right? So
it's-
that there is a cycle, right? So 2 maps to 3, 3 maps to 4, and 4 maps back to 2.
Yeah.
Okay, where does 5 map to?
6.
So 5 maps to 6, and where does 6 map to?
5.
Alright, great, so that's another cycle.
And
Okay.
then you have 7 and 8, which are just on their own.
Exactly, right? So here, how many cycles do we have?
5.
5.
So the number of cycles, which you know this from 465, is
Yeah.
5, right? Alright, this is what we're going to call the number of orbits.
Oh,
Alright.
that's an orbit. Okay.
It's very intuitive, right? Here's an
Yeah.
orbit, here's some element orbited by
Yeah.
itself, here's another group of elements orbited by itself, here's another group of elements. And so what you're doing is you originally taken apart something that looks like this. So It's a little tedious. 7 and 8. Something that looks like this, and transform it into this. This is what's called a group action. It's just nothing more than a function. Make sense?
Yeah.
All this makes sense so far? Just this is just for security, you guys.
Yeah.
Okay, great. Okay, so the question is, how big? So I want to ask, how big is this? How big is this in S in 8? How big is this?
Is it 5?
Very tempting. Very tempting to say it's 5. So why is it very tempting to say it's 5?
Well, I'm observing the only ones with an actual like cycle that doesn't. It's not
So
like a
wouldn't it be
self
2?
cycle. I just felt like. Okay, suppose that 2 is the identity element.
Okay.
It would take 2 jumps to map to itself.
Okay.
So
Oh,
this would be 2,
oh, it's 2 plus
right?
1. 1, 2. Wait, no, it'd be 3. 3 plus 2.
For 2 to get mapped to itself, it's 1, 2, 3.
I want to say it's like 8 or 5.
It's neither.
Is it 3?
Oh, is it 3 because it's the maximum number?
It's not 3.
Oh no, it's 1. It's 1.
Yeah,
It's
that's
not.
Wait. You said it was the
Yeah, you
minimum.
said it was
very
minimum.
intuitive. It's not very intuitive. This is where I don't know how to motivate this. Except I just have to like tell you it and you'll be able to see it.
I have no intuition for it.
There's no intuition. Like
Wait,
this is
you said there's.
Here's a proof.
Wait,
that-
let's try. Let's try.
Dude, he said there's no intuition, bro.
Wait, I don't want to believe it. There must be an intuition for it. Somebody made it up at some point.
There is actually no intuition. You don't have to.
You're just saying this is an arbitrary definition someone just came up with.
It's not arbitrary. I didn't say it was arbitrary.
So then how is it intuitive? Like, how is it not intuitive then?
Yeah, it's either arbitrary or it's intuitive.
Yeah, it's either
And
arbitrary
there's
or
nothing
intuitive.
else it can fall into.
So how many orbits are there?
There's 5 orbits.
Is there?
Are we?
There's 5 cycles. I agree
Oh,
with that.
5 cycles. Oh, are you defining an orbit as something?
I asked the cardinality of that. I didn't ask you how many orbits you had. I asked the cardinality of that. Do you know what that means?
It's the
What is this stands for?
the size of it.
What does that stand for? You have this to the first power, this to the second, this to the second power, and so on and so forth, right? And you stop somewhere. So I'm asking, what is the size of this?
What's 2?
Just because I stopped at 2 doesn't mean it's 2.
No, because there's 2 things with multiple elements.
Actually, really?
There's 2 cycles with multiple elements.
Would it be 2 power 5?
See, I can see how it's tempting for you guys to think it's 5, right? Because you can really
Yeah.
rewrite the cycle as something like this. Do you agree?
Yeah.
So it's very tempting to think it's 5. The question is, how many jumps does it take for you to get from the start back to the start?
1, 2, 3, 4.
5.
It takes 5.
Yeah.
Wait, I don't even understand. How can you get from 1 to anything else?
Yeah.
Are you trapped there? It's a cycle within itself.
So the issue is that the notes are like very proofy, and the proofs are like, the number of these orbits is related to like a huge like plus minus 1 formula that I don't want to prove right now, right? So then like she takes like a general term of like an orbit, and nobody understands, by the way, and then she tries to be like, okay, then it's sufficient to show that there's like some identity element, and then the identity element is like not 5. And I was like, okay, that's bullshit, right? I think it's 5. I think my notes are actually wrong. I think it's 5. Why? It takes 1 hop, 2 hop, 3 hop, 4 hop, and 5 hops back, right? So I think it's 5, which is just equal to the number of orbits.
Oh.
Wait, so what did you say?
But the notes say something like this, and this is the theorem that takes like 30 minutes to prove. Number of star orbits in n is equal to plus minus 1 plus number of ij sigma orbits in. So this is why I tell Nikhil, like, it's not that I don't believe he can do 296, it's just like the notes are very confusing.
Bro, I would have never known.
You would have never known that. I would.
There was no way else to
I
tell
can,
than that from
I
my
can give you the
intuition.
proof, and you'll be able to see why the proof is the way it
number
is.
of clean orbits is plus or minus 1 plus. Wait. Could you explain that thing?
How many ij orbits are here? 1, 2, 3, 4, 5, right?
Yeah.
So it's you take this number and
Yeah.
you do either plus or minus 1. So plus 1 is either 4 or 6. So you can either get 4 or 6.
Yeah.
There is no such. So this cardinality stands for this. Make sense? The number of sigma orbits in n. Cool? So it's either 5 plus 1 or 5 minus 1. This has zero intuition. But the intuition that they're giving us is like saying, oh, what if you connect the dots together, like, and then they give you like a bunch of whole mapping, which I don't even want to go into because it's gonna confuse you. It's gonna be like a bunch of functions, function composition. So I don't want to go into that. But as long as you understand the idea that there's sigma to the first power, sigma to the second power, sigma to the third power, sigma to the fourth power, and sigma
And
to the fifth power.
eventually it must return to
Then
itself.
eventually must
because
return.
it's cyclic.
There's exactly 5. I'm fine with that. Right? Does that make sense? I'm fine with that. Everything else, this is a theorem that it's gonna take a while for you to understand. This theorem took me like an hour and a half to understand.
Fair.
And I still don't understand it. Because
Nah.
clearly I can't explain it right now.
I think I'm
I was like texting my mom and